The next step now is to infer the model. As usual, the story goes that we propose a generative model, a probabilistic model on our data. That was the probabilistic matrix factorization model of the previous slide. Now the problem is that we have some data. We want to do the inverse problem of inferring the model parameters from the data. So this might lead to a question in the context of what we've been discussing in the previous few lectures. We have a matrix M, and it has many missing values in the matrix, and we want to predict what the missing values are. 2 lectures ago, we discussed exactly that problem of doing inference when we have missing values, and we saw there that we needed to do an EM, or EM was going to help us out. So now the question is, do we need some sort of an EM algorithm in this scenario? And so let's think through this problem. Let's let O be the observed part of M, and M subscript M be the missing part, so using similar notation as 2 lectures ago. Then what we want to do is we want to maximize the likelihood, in a sense, of the observations that we've seen given U and V. And so we also have a prior here that I'm ignoring for the moment. And that's equal to the integral of the over the missing values of the complete matrix given U and V. So the question now is whether we need to use an EM algorithm where we introduce this missing data to the model. To answer this question, let's recall that EM is simply a tool for maximizing a marginal likelihood where there's no missing information. Therefore, we only need it when we have the situation that this is hard to maximize, but this is somehow easy to maximize, and also the posterior is known. So if we can maximize this term without any problems, then there's no need and really no point in doing EM. If we can get closed form updates, for example, for this, for doing maximum likelihood, or in our case it's going to be maximum a posteriori over U and V of this likelihood, then EM doesn't bias anything. So we have to look at what does this likelihood look like. So to test how hard it's going to be to maximize the joint likelihood of the observations of the user locations and the object locations over U and V, what we have to do is do the following 3 steps. We have to write out the joint likelihood. We then need to take its natural logarithm. And then we need to take derivatives with respect to all the things that we want to update. So we want to update UI, and we want to update VJ, the user location for user I and the object location for object J, over all the users and all the objects. We want to take these derivatives and see if we can solve them. And if we can, then we can do that without having to introduce EM. For the probabilistic matrix factorization model, we notice that what we can do is write this joint likelihood in this way. We can write a product over all of the observed ratings that we have in our data set of the rating that user I gives to object J, given the user location and the object location for that rating, times the priors on those locations. So remember that the user locations were all IID from a distribution, as were the object locations, and so the prior factorizes into this product over the individual priors. And so by definition, we can write out each of these. This is a Gaussian, and these are all also Gaussian. So we take this likelihood, we take its log, and we get the objective now that we're trying to maximize. So what we want to do when we do map inference, maximum a posteriori, is to find the values for the matrix U and V that maximizes the log of the joint likelihood. And in this case, we get this form where we sum over all of the measurements in our matrix M, the log of the likelihood of each individual measurement given the locations for the user and object, plus the sum over all of the logs of the priors. So we'll plug in what these distributions are, call this objective L, and what we find is that L is equal to this. So we have negative a sum of a squared error term minus these additional regularizations. So this is the log of the joint likelihood when we plug in. And these squared terms all come because these are Gaussian distributions. Remember, this is a Gaussian distribution where we assume that this was generated from a Gaussian with this mean, and so that's how this form comes about. And these are all independent Gaussian priors with zero mean, and so that's where these terms come from. UI has zero mean, Vj has zero mean prior. Now we want to see whether we can actually update these parameters, whether we can update the vector ui and vj by taking the derivative and setting to 0. So we take the derivative with respect to ui, and we find that what we get is a sum over all objects that user I has rated. So remember this notation. We sum over all of the objects that are in the index set of the user I's ratings of this term, minus this additional prior on user I. Similarly, for object j, we sum over all of the users who have rated that object of the derivative of the first term with respect to vj. So we take the derivative of this term with respect to vj. We end up with this term. We take the derivative with respect to the prior. We end up with this term, and we set them all to 0. And we see whether we can solve. And it turns out that for this problem, because of the specific model structure that we assumed, we can solve all of these things. And so the user I's location can be updated using this equation, and object J's location can be updated using this equation. So notice that what we have here is an outer product for user I. We have a sum of the outer product of all of the locations of the objects that user I has rated, plus this additional term. We take that matrix and invert it, and we multiply it by the vector we get by taking the location of each object that user I has rated and multiplying it by the rating and summing those up. And that's the update for UI that maximizes the objective. However, notice that if we wanted to solve for all UIs and all VJs simultaneously, we would not be able to do that because the update for UI involves V and the update for VJ involves U. So we can't say that this value for UI or this value for VJ is the optimal one because it depends on the other parameter settings that we have. So what we're going to end up having is a coordinate ascent algorithm like we've been discussing for the previous few lectures.